So in this example, we're going to use the Tresca and von Mises yield criteria to determine the factor of safety on a rod that has a yield strength of 40 kpsi. It has a diameter of 1.5 inches, and it's loaded. It has a force of 6,000 pounds, a moment of 5,000 pound-inches, and a torque of 8,000 pound-inches being applied to it. So the first step we're going to do is we're going to determine the state of stress at a point. So we're going to look at take a look at a stress element on in our system. So we're going to call this point A. All right, and we want to determine what is the state of stress at point A. If we look at our element at point A, it could potentially have three stresses. It can have a shear stress. It can have a axial force or axial stress or bending stress along the x-axis, and it can have an axial stress along the y-axis. Right. So what we need to know is what is sigma x, what is tau xy, and what is sigma y. Okay. So based off of the loading cases, sigma x, right, we can say is going to be the superposition of our bending stress plus our axial stress. Okay. All right. Sigma, there's no force acting directly along the y-axis, so we can say that sigma y is going to be equal to 0. And then the tau xy, we can say is going to be equal to T R over J. So based off of the problem information and the loadings, the bending stress we can write as being equal to MC over I, and then the and I guess actually point A, based off of how the diagram is drawn, should be on the bottom of the part here. Right? So it should be equal to MC over I plus force over the area for our sigma x and TR over J. So we're just going to plug in all of our terms here to solve for each of our components. So we'll start with our shear stress tau xy. So the given torque in the problem statement was 8,000 pound-inches. The radius in this case would be 0.75, or we can say 1.5 inches over 2. And then the polar moment inertia would be equal to pi over 32 times the diameter of 1.5 inches to the fourth. Right? So if we multiply all that out, what we end up getting is we end up getting 12.1 kpsi. Okay, so we can repeat this process, or we can solve for sigma bending next. So for sigma bending, we can say that would be our moment. Our moment, which was given to us, is 5,000 pound-inches times c, which is the distance from the centroid. In this case, it's just going to be the same thing as the radius. All right, and then in the denominator, we would have pi over 64 times the radius times the diameter to the fourth. Okay, so if you do all that out, what we end up getting is we get 15.1 kpsi. All right, and then the last one is we get sigma axial. All right, which is going to be just the force over the area, which in this case the force was 6,000 pounds. that was given to us in the problem statement, and then the area was it's just pi over 4 times the diameter squared. All right, if we do multiply all that out, we get 3.40 kpsi. Right. So then we can, using this information, we can draw out our stress element. So we end up getting our tau xy is going to be 12.1. All right, our sigma y, our sigma x is going to be equal to 15.1 plus 3.40, so that should give us 18.5. All right, and our sigma y should be equal to 0. Okay, so that's our given state of stress. For at point A, which is probably going to be the highest state of stress along the rod. So the first thing that we need to then do is, using the state of stress, or the next thing we can do is we need to find our principal stresses. All right, so we know for a 2D state of stress like this one, we can say that sigma p would be equal to sigma x plus sigma y over 2 plus minus square root sigma x minus sigma y over 2 squared plus tau xy squared. If we plug everything in to this equation, we end up getting 18.5 over 2 kpsi plus or minus square root of 18.5 kpsi over 2 squared plus 12.1 kpsi squared. And so we should get two values for our principal stresses. We'll get sigma p1 is going to be equal to 24.5 kpsi, and then sigma p2 is going to be equal to minus 5.98 kpsi. Okay. All right. So what we can then do is we can solve for and once we have our principal stresses, we can then solve for our von Mises stress, and we can then solve for our Tresca, or our maximum shear stress. All right, so for sigma von Mises, all right, we're just going to plug into our von Mises stress equation. So from earlier in the lecture, we know that the sigma von Mises is equal to this equation here. So we can plug in, so we know that sigma P3 is going to be equal to 0. All right, well, technically this is really sigma P3 and sigma P2 is 0. So we can plug in all of these values here. So we're going to get 1/2 sigma P1 minus sigma P2 is just going to be equal to sigma P1, so it's just going to be equal to 24.5 kpsi minus 0 squared plus sigma P2, which is 0, minus sigma P3, which was equal to negative 5.98 kpsi, all right, squared, plus sigma P3, which is equal to 5.98 kpsi, minus sigma P1, which is going to be equal to sigma P1 is 24.5 kpsi squared. All right. So if we plug in all of these all these numbers, what we end up getting is we end up getting 28. Sigma von Mises is going to be equal to 27.97 kpsi, which is just 28.0 kpsi. All right. So the next step we can do is we can solve for our maximum shear stress, or our Tresca stress, which we know is just going to be equal to sigma P1 minus sigma P3 over 2. So in this case, sigma P1 is 24.5 kpsi. Sigma P3 is equal to negative 5.98 kpsi. All right, we just divide that by 2. So we should end up getting tau Tresca to being 15.24 kpsi. All right, and then the last step here is we're going to calculate the factor of safety. Using the von Mises criteria and the Tresca criteria. So we're going to use 2 sets of equations to do this. Let me paste those in real quick. So we can rearrange these 2 equations to solve for n. So we take our first equation. What we end up doing is we can just set this to be an equal sign here, and so we can say that n would be equal to sigma y over sigma von Mises. All right, so if we plug in our sigma y, which was equal to 40 kpsi, and we divide by our von Mises stress, which was 28.0 kpsi, we end up getting a factor of safety of 1.43. Right, and then we can do the same thing. We can take this equation here. We can rearrange and solve for our safety factor. N would be equal to our yield strength over 2 times the maximum shear stress, or our Tresca shear stress, which we calculate to be 15.2. So we are just going to plug in our 40 kpsi yield strength divided by 2 times 15.24 kpsi. And we'll end up getting 1.31 for a factor of safety. So what you can see here is that in this case, for our combined normal stress and combined with a shear stress, in this case the Tresca, because the factor of safety is smaller, is more conservative than the von Mises criteria, right? So this is the general procedure you could use to find the factor of safety for a given part. We already did an example problem where you could do where you could find like the maximum allowable applied load. And the only other thing would be is if you're given desired factor of safety and you're given the loads that need to be applied to a system, you can also design for the geometry. So you could design for like the diameter of a given part. Okay. So just to recap what we did in this problem, we first were given a loading situation, and then we had to calculate the system, the state of stress within the system, which we did here. And then using that state of stress, we could use our principal stress equations to solve for the principal stresses at that point. And then with the principal stresses, it's really easy to solve for our von Mises stress and also our maximum shear stress, or our Tresca stresses. And then once we have our principal stresses, or our von Mises stress and our Tresca stress, it's really simple to apply those factor of safety equations in order to solve for the factor of safety in this case.